Ladies and gentlemen, please welcome our Deputy Vice-Chancellor, Professor Jeff Rogers.
So good evening, ladies and gentlemen. As I say, I'm Jeff Rogers, I'm Deputy Vice-Chancellor for Research and Innovation, and I'm delighted to welcome you here for tonight's lecture, the second inaugural lecture in the 2017 series. As the person responsible for research here at Brunel, these lectures are particularly close to my heart. They celebrate and showcase some of our best research and demonstrate the wide variety of research that's taken place across the campus. We're very proud of the impact of our work on the public and on the local community, and we're delighted to share our interesting research with many staff and students and the local community at these events. Tonight's lecture will be given by somebody I regard as a close friend, Akram Khan, who's a professor of particle physics and e-science here at Brunel. His field of research combines the fundamental with the applied. Over a long career, he's worked at most of the leading national laboratories in the world, including DESI in Germany, CERN in Switzerland, and SLAC in the United States. After reading mathematics and theoretical physics for his bachelor's degree at St Andrews, Akram went on to complete a PhD at University College London in experimental particle physics. He then worked as a European Research Fellow at CMAT in Spain and CERN in Switzerland, as a senior fellow at both Edinburgh and Manchester universities, and then had a faculty position at Stanford, and then came to us in 2003. We were very lucky to recruit him. Akram has a very strong and keen interest in public engagement in science and has served as the university's public engagement ambassador for the last 4 years. He's led by example, been involved in many activities to help bring science to a wider audience, organised many activities and participated in many himself. His radio programme with Will Self, where they walked around the 27-kilometre Large Hadron Collider, was very popular, huge number of listeners, and received many very positive reviews. This included a review in The Guardian by physicist John Butterworth, who said that he felt the discussion was like something out of A.A. Milne, with Professor Khan playing the role of the enthusiastic Tigger, and Professor Self, the disbelieving and doubtful Eeyore. Akram has published extensively. His recent research has been addressing the fundamental questions about the difference between matter and antimatter, and understanding new exotic physics processes that might help identify some of the problems with the standard model. He's currently developing a novel particle cancer therapy machine and working on the next generation of internet technologies, some of which he'll speak about tonight. So the lecture will run for about 45 minutes. We'll have some opportunities for some questions, and then followed, I hope most of you will be able to join us for refreshments in the atrium after that. And so it gives me very great pleasure to welcome Akram to give his lecture entitled Journeys into Fundamental and Applied Knowledge.
So thank you very much, Jeff, for that. That's absolutely wonderful introduction. And thank you very much to everybody for coming to this lecture. So I'm going to try something new for this lecture. I'm not going to give my public talk that I normally give for particle physics and trying to abstract things that have been done and things that would be done in the future. So what I'm going to try and do is split up the lecture in 2 parts. The first part, I'm going to read something to you that I've written. And I think it's very, very critical and very, very important sometimes to write your thoughts and let the form in which you express them take over the content. And sometimes it's very important what the content is as well. And I think the latter part will contain the content, and I think the first part will contain the form or the spirit in which I want to actually articulate about the importance of our journey into the realms of fundamental and applied science. And I think it's very, very important to be able to disentangle and then merge the two together. So I think that's how I'll do it. Is everyone happy with that? Right, let's do it. And if not, tough. right? But there will be a leak motive principle. You see, something will run all the way through. These are not disjointed. And there will be things like, questioning, curiosity, and important, the question why. So one of the first words we learn as a child is why. We want to know something about this radical mystery into which we have been unwittingly cast. We want to understand it all of how it works, and we feel a deep existential need to engage with the others with whom we share this world. And so after the first babblings and cooings, we begin to ask the question, why? And then we never stop. Very soon we find that curiosity is seldom rewarded with meaningful answers that satisfy, and all we're left with is an ever-increasing desire, insatiable, to keep on asking questions without end. Perhaps the sense of curiosity comes fully alive in asking the question, what do we know? We find that when we know, what we know is full of holes, and so we enter in a state in which we're compulsively questioning the territory through which our mind is passing and is passing still to come, with eager anticipations of the uncharted country ahead. Evolutionary theory tells us that human imagination is an instrument of survival. We developed the ability to represent outer reality in symbolic form within the mind, and to conceive situations that we might confront before actually encountering them in the world out there. Conscious of ourselves and of the world around us, we are able to build mental maps of these territories and to explore them at will, choosing those that we feel best meet our needs. We imagine in order to exist, and we are curious in order to feed our imaginative desire. Imagination is an essential creative activity, develops with patience, not just through successes, which are conclusions, and therefore tend to still the questioning or the questing mind, but most productively, imagination develops through failure, through attempts that prove to be mistaken and require new attempts that will also lead to failure further on. The history of art and literature, like those of philosophy and science, are the histories of enlightened failures. Fail, try again, fail better, was Beckett's lyrical summation. But in order to fail better, we must be able to recognize imaginatively those mistakes and inconsistencies. We must be able to see that this or that combination of words or colors or sounds or numbers does not approximate well enough to the inspired vision of the mind. But all the while, though these few moments of triumph and those many and many more defeats recur the greatest question of the imagination, why? Our education system today, by and large, refuses to acknowledge this unending quest to penetrate ever deeper into the sublime beauty below the surface of things, driven by the imperatives of providing accreditation for those taught to value little else than material prosperity and financial gain. Our institutions of education no longer foster thinking for its own sake through the free exercise of the imagination. Schools and colleges have become training camps for skilled labor instead of forums for questioning and discussion. And as Francis Bacon would say in the 16th century, which he called the merchants of light, we learn to ask how much will it cost and how long will it take, instead of asking why. Why, in its many variations, is a question far more important in its asking than in the expectation of a final answer. The very fact of uttering it opens up numberless possibilities, can do away with preconceptions, sums up endless, fruitful doubts. It may bring in its wake a few tentative answers, but if the question is powerful enough, none of these answers will prove all sufficient. Why? As the young realize early, is a question that implicitly places our goals always just beyond the horizon. And I think that's extremely critical, the fact that we ask why. Because there is a misconceived notion that when we see things, or seeing, or this phrase, seeing is believing. And in fact, the critical thing is, what does seeing really mean? And the way that we see things is through only a small 5% of a thing called the electromagnetic wave. So whatever we see is just this part. Everything else is a darkness, or they are hidden from our visible senses. And what we do then to enlarge this is to develop technological devices to be able to see a much more broader, a broader visual representation of reality that's out there, and then have some representations to create meaning from them. And I would argue that actually we have an extended vision now. We've gone beyond just seeing with the visible. We've got some wonderful devices, from the LHC to radio telescopes. And in fact, also, I think we've got mathematics to blend, to create the synergy of trying to create meaning. And then we can combine this with our senses to be able to see maybe new realities, a bit like Alice in Wonderland, when she went through the looking glass with a certain perspective or a certain way of looking at the world. And what you end up with is a much more richer and a much more nuanced way of perceiving reality. And I think the way that I would like to sort of explore this idea is with questions that have been quite central to my career. Right? So I think we're going to go through one by one certain questions which then would highlight, I think, some very, very fundamental principles about reality. And the questions are very simple. I mean, the very simple question, for example, of what is a proton made up of? I mean, we're all made up of protons in one way or another, because they're all made up of atoms. But what is it? I mean, what are we made up of? And that begins to ask the question, what is everything made up of? And if you look at the human scale, well, we know that for a physicist, it's just made up of three basic elements, basically water. That's what it's made up of. And a lot of, sort of goo in between. If you look at the Earth itself, it's mostly oxygen of one sort or another, right? So what you're seeing is, as the scale gets higher, the actual simplification, the world looks more simple, or the universe would look even more simple. Because if you're trying to describe matter in the universe, it's just these basically helium and hydrogen. That's what we see. But we also know that actually that's only 4% of what we see. 96%, we have no idea as yet what it's made up of. So as the scale gets higher, things become much more easier to actually look at, and it's much more complex at the human scale. So if we go the other direction, we know that DNA molecule is a very, very important molecule, and it gets articulated or expressed, and we get our own characteristic from it. But it's really made up of some atoms, and the atoms, we know, are made up of a nucleus with electrons going around in fixed orbits, and this is at the scale of 10 to the minus 10 meters. And then if you ask yourself, well, what's the nucleus made up of? Well, the nucleus is made up of protons, which is what we're after, and neutrons, and is held together by this force called the strong force. And this is at the scale of 10 to the minus 14 meters. But then you can go even further, and you can say, well, what is the proton made up of? And in our model, we have the proton here. So the protons could be made up of small particles we call quarks. So they're the smallest entities that we know about at this present moment, and they're held together by the strong force. So there's two types of quarks, which we call the up quark, and one is the down quark. That's what the proton is. And the neutron is the opposite. So that's one up quark and 2 down quarks. So this is what they're fundamentally made up of, these basic entities. And then there's the electron. So the basic constituents of matter, the smallest we can go and look at, is 1 electron and an up quark and a down quark. And we can describe with that all of reality around us. Everything is made up of those. So now if I take my proton, I pretend these are the up quarks and this is the down. So if I take 2 protons and 2 neutrons, and I give it enough time, so say that they were around at the early stage of the universe, and time goes on, because there's lots of infinite time. These will come together through some forces, and you will create stable atoms. And if you have 2 electrons going around 4 of these protons and neutrons, you would end up with a helium atom. And if you give helium enough time, say you give them billions and billions of years, right, which is enough time, a lot of time for them, what you end up with is the universe that we have to some extent. So we can actually map out, not in particular, but the general pattern, the mathematics to be able to facilitate that, we can actually write on a board somewhere. So we can understand that relatively good. Well, so the way to test this is you always need an accelerator to be able to test and go inside the nucleus. And this is where I did my PhD. So I worked on in DAISY, which was the very first accelerator to use an electron, which is accelerating in one direction, and a proton, which is accelerating in the other direction. So since the electron is a point particle, it can act as a probe. So you have the proton coming, and the electron hits the proton, and it can actually probe and see what the proton is made up of. So it's a wonderful tool to do this. And this is the accelerator. You can see it's about 6 kilometers in circumference here. And the experiment that I worked on was Zeus, which was here. And we accelerated and smashed particles together. So I was involved right at the start, at the construction phase. So this is when we had built the accelerator, and we were about to close it, which is very exciting. And you can see me here. Who can see me? The hair is long, but the color has changed only. So this is me, very proudly standing at the back. And in fact, this was one of my responsibilities. This is the device, the tracking system that we developed at UCL. And this fits in the heart of the experiment. It's one of the most important devices, and one that I love very much. So this was an exciting journey. And what we found was that the actual proton that I showed earlier on, which contained 3 particles, 3 fundamental particles, is actually nothing like that. I mean, this is how a proton looks. If ever someone asks you, what does a proton look like? You show them this distribution, yeah? So these are the different probabilities for those particles. And x is the distance that you're probing inside the actual particle itself. So I think it was wonderful. This was part of my thesis. So that was very exciting. So that's one of the questions. From something very basic, I think it gave us some very profound results. The other question that I worked on was this idea about if we believe in the paradigm that the Big Bang was how the universe began and then it evolved, we know that if the Big Bang did come into being, there should have been equal amount of matter and antimatter, right? So we all agree with that. So the question is, how can that be? I mean, we are around, so where is the antimatter gone? So there must have been some asymmetry in the early universe of some sort. And so the question is, is that the case? Well, the first thing you would do is you would use the Hubble telescope to look deep into space and to try and see if you can see, all these white spots you see here are galaxies, to try to see if there's any dark or any antimatter out there in the universe. And we couldn't see anything, which is a shame. So most of what we see is just matter with very, very little antimatter in the universe. And then in the 1970s, there were these 2 theorists, Kobayashi and Masukawa, who sort of came up with this wonderful theory, which actually predicted that there has to be some sort of asymmetry in the early universe. And if that is the case, there are some predictions that one could make about those. And what you do is you try and create some matter and antimatter of a particular particle, and then you follow the dynamics of those two particles. So one is the matter, and one is the antimatter. And you see the dynamics of those two. And if the dynamics are different, you know that there is something different. There are some different physics related to them. So what we did do, so their prediction was that 1 part in a billion, there was an asymmetry in the early universe. So this is my depiction of it. And then obviously it annihilated. And all that was left was this 1 part in a million. To me, this is very, very, I think, very profound to think that everything around us, you and I, and everything that ever existed is due to this 1 part in a billion that exists. And the predictions that these theorists made, we tried to test at the Stanford Linear Accelerator. So this was my work at Stanford. So this is the 2 mile long linear accelerator. So we have electrons whizzing down here, and then they get bent and put into this ring here, and the positrons, the positive electrons, get pushed here, and they come and they collide here. And this is where we developed our detector. So they collide at the center, and they create this new particle, which we can optimize. And then these particles decay into matter, antimatter, and then we can look at the dynamics of those particles. And that's exactly what we did. And so again, this is the collaboration. You can see that the collaboration is getting bigger, yeah? So there's approximately a couple of hundred people working on the DAISY experiment, or the Zeus experiment. And in Stanford, on the Barbar experiment, there's about 500. Not everyone's here. But who can recognize me here? Yeah?
You're going more grey.
Got more gray, yeah, that's me here. I had a haircut. Yeah, you can see the evolution, yeah, of that part. So yeah, and this is the UK contingency who are part of this. And in fact, the detector we developed is proudly shown behind here. And this is the, I'm not as tall as that. There was a sort of a stool that I was standing on. So that was kind of another exciting experiment. So what we did do on the physics side, we did capture those two wonderful matter-antimatter particles. And now we're going to see if there's a difference between the two or not. So from my work, so you'll see a plot here. So what you see here, the red point, or the red dots here, is the antimatter particle, and the blue is the matter particle. And you can see a beautiful difference between the two. And if you subtract the two histograms, what you get is this oscillatory term. And this was exactly, I mean, this was never done before. It's the first time it was ever done with this particular particle. And this was the first time we measured the asymmetry between matter and antimatter in the universe. And so obviously, you know, since theorists put forward wonderful theories, there were these two individuals, Kobayashi and Masukawa, who were given the Nobel Prize for 2008. And they did mention and sort of mention us that we did do the results. We didn't get the Nobel Prize, but we got mentioned. So that was good. So that's another question. So another interesting question which has driven my interest has been this question of, you know, how is mass generated? Is an interesting question, because even when you're breaking your particles or your matter particles down to the smallest level, you can still say, well, actually, so how did they get mass? How did the quarks get mass? Where did mass come from? I mean, who gave us mass, man? No idea. So that's something we got to think about. And then we can ask an even more profound question, yeah? I mean, you got the mass. Is it related to the fate of the universe and the structure of the universe, yeah? So these look very different, but actually, you know, are actually related in a real sense. I mean, the way that we think about mass is, I mean, everyone is massless, yeah? We don't have any mass, which is a good sign, man, so that's nice. And the way that we acquire mass is when we interact with something. So the smallest particles, like the quarks, they whiz around masslessly. But then we say, well, in the universe, in the vacuum of the universe, there is a field, there is a wave or an energy field that exists. And it's the interactions of those subatomic particles with the field that actually makes us go slower or faster or something. And that's what mass is, that drag as you interact with the energy field, right? So that's that's a hypothesis in the early 1960s that was put forward. And then you say, well, actually, if there is a field in the vacuum, then the field can wobble, right? It can oscillate. And each oscillation for this field corresponds to a particular particle, right? So in this case, we say it's the Higgs field, named after its inventor, and it's a field that permeates space. And each time it wobbles or you hit it and it perturbs, that perturbation is the Higgs particle, right? And since we also know that there is a field in the vacuum, which means you take everything out, it still exists. This field is a part of the underlying structure. You can't get rid of it. Then it must have some relationship with the structure of the universe. There must be some sort of relationship with it. And if it has some sort of relationship with the structure of the universe, then maybe there's also maybe it also governs the fate of the universe as well. Maybe there's some sort of relationship with that as well. And I think there is, and I'll try and show it. So here's my slightly technical diagram, yeah? So here's my Higgs. Higgs particle will always sit here at the lowest point. So that's the particle that we measure at CERN. But the question is, that's the perturbation, but we said that it's a field, right? So it's a permeating field. And any field has a potential energy associated with it. But we have to work out what the form, the analytical form of that energy is. So there could be various things. We know this because we've measured it, but how do we know how it looks? How does the field analytically look? So if the field is like this, we can put that into our equations and we get a stable universe. If the field goes like this, it's stable. But the minute it goes up and it goes down, you get another minimum here. So you got a minimum here and a minimum here. And most things in life, most dynamic systems, like most of us, we always want to go to our minimum. We never want to go to anywhere else. So in reality, if this was our field, this one that goes up, and then goes down here, this minimum is less than this minimum. So if this is our universe with this potential here, it could be that all our universe wants to do is tunnel into this universe. So any moment, it could quantum mechanically tunnel into a different state of being. And mathematically is correct. Experimentally, we've verified the principle called quantum tunneling. So this potentially could happen. So the thing that really excites me is that what we need to do is we need to look at the physics of the Higgs potential to actually tell us something about the structure of the universe and its fate. And the way to do this is to take two types of physics. So one will be the Higgs physics, which we'll look at, and the other will be another fundamental particle called the top quark, right? And I'll call that the top physics. And in fact, at Brunel, we've been involved in both of these activities. And if we measure the mass of the Higgs particle, which is about 125 here, and if we measure from top physics the mass of the top quark, it comes to about here, somewhere in the middle here. And it sits here. So this is approximately where the crossover is. But then you can say, well, okay, I've given you these two values. Now I'll put that into our theory and see what the predictions are. And these are the predictions as to what state the universe is in our universe. So what we find is that it's close to a metastable or a stable. So what we need to do is try and reduce the error bars on this measurement such that we can say statistically significant, whether we live in a metastable universe or a stable universe. So if you want to do that, you need to go and build another massive accelerator. So the Large Hadron Collider you can see here is about 27 kilometers as opposed to 6 kilometers that the DAISY accelerator is. And our experiment, which is the CMS experiment here, the compact muon system is here. And we accelerate protons. in one direction and protons in another direction, and then we collide them here. And this is our camera, or the CMS experiment that takes pictures about 40 million times a second. It takes these pictures and conveniently then stores them for us to analyze. And you can see it's an incredibly interesting device that does that. And this is the result. So then we start to collect the data. And what you're seeing here is the mass of the particle and the number of events that one sees. And it was animated a minute ago, but what you see are the data points, which are in black. So here you go. So we're collecting data. The red is what we know from theory. So the data should replicate the theory. So and this is the error bars with the data. So you see something strange is happening here. There's a discrepancy in our understanding of nature and the data itself. And what we're going to do is just accumulate data as time goes on, and now it's become really significant. And now you can put into the theory what Higgs told us in the 60s. And what you do is you get a beautiful description of the data itself. And that's how we discovered that wonderful signal. And obviously, again, there's this a wonderful Nobel Prize for Peter and Francois Anglet, who were the two theorists who sort of came up with this idea. And obviously, CMS was mentioned in the citation, which is a good thing, and Atlas. And this is the paper that actually led to the Nobel Prize, which actually gave us the mass of the Higgs, or the mass of this new particle. Again, Brunel was centrally involved in the analysis and the data instrumentations that led to it. Now, this is the Higgs part. We're also involved with the top quark physics. Now, we were one of the first people to actually work on and present our results to the physics community. This was the first measurement of the top quark that we did, and we got a beautiful measurement of it as well. It was a very, very competitive measurement, which is good. This is the results at the end. So what you're seeing, the red is the top quarks, and the green and the yellow are the background associated with it. And this was done with my PhD student who did the measurements, but then I also sort of convinced him that he should carry on and do a second measurements. So he wasn't contented with just doing the cross-section. He also did the differential cross-section, which is a much more interesting way of looking at the phase space that these particles live within. And what was very nice to see, because when your students are writing the thesis, they never show you the acknowledgement, yeah? So it's always, you always go, but that's the first thing that I do, is look at what has he said about me, or what's he said about someone else? And it's very warm and nice to see this. So he said, many thanks to my supervisor, Akram Khan, who really put faith in me and drove me on to succeed. Although, I thought, my God, here he comes. I don't always appreciate being put in daunting situations at times. I have gained real value from it. And that was very touchy, thing, because I told him, I think you should do it. I tried to convince him with my enthusiasm of how it's very, very important, and you're going to make and it's only a little bit of work, in quotes, that he should do it, but he will get so much, it'll be so much more interesting, right? And in the end, it was, and it was a wonderful thesis at the end. So I think he did. That was very nice of him to say that. I wasn't sure he was going to say that. We were also then honored to actually win a competition to actually host a very famous and a very important conference in the UK. And this is a conference which actually becomes the reference frame or the default where everyone that makes references about measurements, about top quark physics, using the results that are presented at this conference. And these are all the experts in that particular field. And this is me. And this is Paul Kybert also from Brunel. So that was an extremely successful conference. We published our results in this journal, and that became the reference where people then quote from. We were also then invited to lead at CERN the cross-section group, the top physics cross-section group, which is wonderful as well. But very important, because that's an international group then. So that was another, I think, a very, very interesting piece of work. So the next question that I'm going to discuss a little bit is, I mean, we've got this wonderful machine at CERN, which is producing a huge amount of data. I was also interested in software. You know, is there some way that we could go beyond what the internet is doing or what the World Wide Web is doing, which also actually had its birth at CERN? Because what its motivation was, how do you facilitate physicists that are, you know, distributed, and how do you give them various documents? So they were just moving of documents. Now, since we've got lots of data at CERN, you know, are there any technologies or middleware or software we could develop which can facilitate that? So again, just to highlight the numbers for you. So we have this proton-proton. It accelerates, or there are. Oops, daisy. Not sure why it doesn't want to do that, but see if it comes on again. These oscillate about 11,000 times a second. And what they do is they create a huge amount of data as well. So the data that's streaming out per year is about 14 to 15 petabytes of data. So it's a huge amount of data that's coming out. And we need about 100,000 computers to be able to analyze the data. And you can't just place all of them at CERN. That's not the way to do it. And you can't place all your data storage at CERN. So is there a way that we could develop some software to facilitate that? And then obviously, you know, we came up with a model of how you can distribute it. So you keep all the data that's generated at CERN as raw data, and then you can stream off part of the data to some national tier 1 centers, so national big computing centers. We had ours at Rutherford, Appleton, so it was a big center. And then we had these tier 2 sites, which were the local sites where certain universities can get together and connect with the national center. But it becomes even more complicated because these are MASH systems. And now you can see how complicated the system could be, and you need to develop software to facilitate that. So what we did was we split up our centers like this. So we had 4 of them. So there's a thing called Scott Grid, which was composed of Glasgow, Edinburgh, and surprisingly Durham as well. Brunel sits in London Grid, which are these universities: Royal Holloway, Imperial College, UCL, Queen Mary. So there was and then we had the South Grid and the North Grid. So we had these distributed tier 2 centers that could get together. And now the problem is, can we develop software such that I, as a user, can access any resources without having password? So if I wanted a certain number of CPUs, you know, compute engines, I should get them relatively easy, or data or whatever that I want, transparently. And so we started a project in 2001, and it went all the way to 2011. And what we did do, we started to look at how can we go from the web, which is moving documents, to the grid, moving data. And we started to develop some middleware or software to make that transparent. And then the next the next part was to actually go from developing this prototype into a production system. And then with the LHC just coming online, we actually made it into a production and exploitable system that was available at the time. So again, you know, we're proudly here on our very first meetings. And this is me right down here. So it's actually quite nice. And these are all the universities. So it wasn't just Brunel or you know, there's a lot of universities that are involved. Fascinating project, absolutely amazing. And this is, and in fact, the project that I was doing was Scott Grid. And Scott Grid, I was the technical coordinator, and we were the first people to actually develop and prototype and get the system up and running. And we showcased it at the opening of the National eScience Centre in Edinburgh, and it was opened by Gordon Brown. And again, you can see happy, proud managers, and the real technical staff is at the back. Absolutely amazing. They come at the right time. And this is the system working now. So you can see there are centers, compute centers all over the world. And what you're seeing in real time is data being shipped across, people's jobs running across all over the world. And it wasn't just for particle physics. I mean, we did it for particle physics like we do most things. You know, we do them for a particular extreme environment. But it has had a huge consequence. I mean, all of these other wonderful activities have made good use of the middleware or the software that we developed for them. Well, not for them, for us, but they could do it. So that was another one. So that was a nice thing, but at the same time, I was also really interested, because protons are very, very interesting, but in trying to see how, we could actually make use of them for cancer therapy. And this was very exciting. We know this sad statistics. Well, I don't know whether it's sad. That 1 in 3 chances over your lifetime, someone is going to get cancer, because we are living longer. And most people that do get cancer, there are 3 types of treatment, where about 40% are given radiotherapy and about 49% is surgery, and chemotherapy is only 11%. And sometimes it's a multimodal treatment that patients get. But I just want to focus on the radiotherapy, because this is one example that shocked me, certainly in 2007. I knew very little about it at the time. But if you look at this horrible form of cancer that's in children, and this is what happens. This is the dose map with X-rays that normally children are given. So you've got to irradiate the spine of the child. And you notice a huge amount of collateral damage that's going on. This red is pretty intense dosage that the child is getting. And there are developing and vital organs that a child has. So, you have to be very, very careful. This is with X-rays. So what would happen if you use protons? Right? So if you look at protons, that is truly phenomenal. There's such a beautiful precision in the amount of dose, and where the dose could be delivered to is absolutely critical. And have we got any proton therapy machines in the UK? Yet we led the field. We led the field of accelerated technology, and we have 0, absolutely nothing. And most of our patients that are sent abroad. And I tried asking the oncologists or the managers, how do you select sending patients through the NHS? And it doesn't work. It's never clear to me as to how it's done. So we started lobbying the government and telling them you should have one, you should build it, man. What does it cost you? It doesn't cost you anything. It's not a huge amount. And over a period of time, they did agree that they would think about building some, and we wanted 3, one as an experimental way of doing it. And at the same time, we also put in a grant bid for trying to do a prototyping, because I think the biggest expense is the size, as most things are. And you want to make it as small as possible, yeah? The accelerator is where the cost is. So if you can make it small as possible, then it becomes a viable thing. And so we made actually, just going back. So why is the proton better? I just wanted to show this. So this is how it works. This is why it's better. So this is distance. On average, a tumor would be about 15 or 20 centimeters inside. There'd be some growth that could develop. Now, if you were given X-rays, this is the distribution of intensity. You can see you can deliver where your cancer is. There'll be some sort of dosing. But look at all the collateral damage you will get. So most of the radiation, intense rate, in fact, what's even worse, you could cause cancer. Not cure it, but cause it, because most stuff is going to be here. You're going to be irradiating in some way. But look at the proton. That's a beautiful thing. This is called the Bragg peak. And it sort of deposits exactly where you want the full intensity to go. And again, it's protons. So you see protons are incredible. And so we made a bid in 2007 to the Basic Technology Fund. And surprisingly, it wasn't a huge process or a huge proposal that we wrote. It was only about a few pages, but for some reason they said yes. And we were given about 7 million, which mostly went into hardware, to actually build a machine at Daresbury to actually do it. And at the end, I won't go into the detail, but at the end we came up with this conceptual design, very, very novel, very small, something that we could actually build, never been built before, type of machine. I'm pretty proud of one of my students who finished his thesis working on trying to develop a conceptual design report for this system. It actually got mentioned in the highly respected journal, the Daily Mail, and in a nice way, so that's very nice of them. But more importantly, one of my students did a huge amount of work on it. And of course, we had royalty as well, coming to sort of look at the very novel fixed field alternating gradient magnets, new form of magnets. And this was our final paper. So this is the conceptual design for this particular novel way of looking at things. And again, I think I'm very proud that Brunel was centrally involved in sort of developing the concept. And now it has to be taken up by some entrepreneurs to actually try and get this up and running in some way. So that's another wonderful thing. So the other thing is, the last question I just want to sort of go on is this question about the wondrous journeys of human beings. Yeah, I mean, we all, and I think the darkness is the appropriate place. That is where wonder exists, in nothingness, in the vacuum, in emptiness, from where the Higgs actually gave birth to our universe. And in fact, it is what gives birth to our creative juices to a large extent. And I think, I mean, this is where Will comes in, because I got to know Will in 2011 or 2012, and he had this wacky idea, which I thought was trivial. I thought, what a waste of time. But I went to the meeting anyway, because it's organized by Teresa. So I went to it. And actually, the more I listened to it, the more interesting it became. There's a wonderful story by Kafka, the country doctor. And nothing happens. A country doctor goes to a patient, and that's about it, yeah, to see if he's got some issues that he's got to deal with, yeah. Right, nothing else, yeah. But it really is everything. That's just trivializing it. It's very metaphysical. It sort of takes you into places. I mean, in fact, it boils down to it's what humanity is all about. In that short story, you get a beautiful depiction of what it means to be human. And so we started this, and so Will wrote this wonderfully long essay, which actually did capture all the other people's contributions. And the nice thing was that a lot of us, Peter as well, I see in the audience, and many other parts of the university were involved, and we did actually begin to develop something very interesting, something very dynamic. In fact, looking at something from a prismatic point of view, where each of us shone our own perspectives on there. And in fact, we actually, with Jane Wilton, we symbolized what this wound could be. It could be, what all galaxies or universes came from, which is from the black hole, possibly. And we thought that would be an appropriate representation of that, because it's the death as well as the birth of something new. And so we, and I don't know if it's important, but certainly it also, well, it's very important. See Jess in the front. It became an impact case, yeah, which was absolutely solid and got presented, and I think it was very well received. So I think that's another wonderful unforeseen consequences. But what I also would like to do is just to play to you something that we did. So we made all this concept of a black hole, and it was, I mean, I think Jane's not here. She couldn't be here. Ah, she is, Jane. Nice to see you here. She is an amazing artist, honestly. Sitting with her and trying to teach her quantum cosmology and black hole theory. I mean, she would come back with real interesting ideas, and it was to do with ice, layers of ice. She could spend hours doing this, telling you the layers of ice and chemicals that went into it, and photographs that were taken of intervals, and mashes that were put in. And what you're going to see is a bit of that, and I think we should see it. I think it's an absolutely wonderful thing. And Will's going to have a voiceover to it, so if you could turn the lights down, please.
Yes, indeed. The young man is ill. On his right side, in the region of the hip, a wound the size of the palm of one's hand has opened up, rose-coloured in many different shadings, dark in the depths, brighter on the edges, delicately grained with uneven patches of blood open to the light like a mine. That's what it looks like from a distance. Close up, complication is apparent. Who can look at that without whistling softly? Worms, as thick and as long as my little finger, themselves rose-coloured and also spattered with blood, are wriggling their white bodies with many limbs from their stronghold in the inner part of the wound towards the light. Poor young man, there's no helping you. I have found out your great wound. You are dying from this flower on your side.
I mean, that is true. Give the lights back on. I mean, I think that is an amazing, I think that's absolutely wonderful, wonderful work that was done. And I think you have to give yourself, yeah? You have to sit back and say, well, actually, the next it goes on, by the way, that's 12 minutes worth of stuff, which is shrunk here, right? So please go to the website and just sit back and just, relax. You're not going to do anything for the next 12 minutes, so think about nothing. Just look and feel and connect in some sort of deeper way with it. And you'll see all sorts of wonderful images, and maybe more of yourself within that. So I think that was a wonderful project that brought together the university, or brought together people from different parts of the university in, I think, creating something very unique. And I think this emergent knowledge that we got from that was very special. And I think that was wonderful music by Peter. Peter Weigel did the amazing back music that went to that piece of work. Thanks, Peter. That was wonderful. So we didn't just finish there. So also, I think Will and I had two other journeys. It almost reminds me of Dante. Yeah, we went through two other journeys of our miserable souls. So first we went to CERN, and we said, well, okay, we're going to go through different ways in trying to explore the nature of being, in my opinion, or the nature of what wondrous thoughts could emanate from the scientific enterprise. So first we said, well, we'll go around, walk around the 27-kilometer ring, which is approximately 50 kilometers if you're going to walk. And then every now and then we would go underground 100 meters into the experiments and see what these individuals are beavering away at and what are they trying to do. And the other thing that we did was it was Maxwell, James Clerk Maxwell's anniversary of his famous paper 150 years ago that he wrote in 1865, which actually gave us 4 equations, which are the foundations of electrical and electronic engineering. So that's our whole degree course. But I think of all of technology, to some extent, is based upon 4 equations that Maxwell wrote here. So we went on this journey. And also, it was a critical thing, because that's when, in the history of ideas, especially the scientific ideas, things began to become more mathematized. And the things that he did develop actually were led through the beauty of maths and the representations that maths could have for the real world. But you can listen to the programs to actually do that. But there is one other thing so we've got these absolutely wonderful. I mean, I think they're almost like cantors. I mean, Lawrence Grisel was the producer, and I think he made these wonderful 5 very short, about 10 to 15 minute long extracts, and they're small pieces of poetical brilliance. So these were the 2. Now, Will also did very little work technical work for the first one, right? He just turned up as is need, and he goes around and walks around. And I think that's right, because you should not have to do all the maths or all the background reading to do it. You should just feel it and see how you interact with it and see what it makes you think. But he was criticized for that. So for the next one, in particular for the Maxwell thing, it's much more technical, right? Because you've got to understand some maths. And, to be fair, he did go for a week and spend time with a tutor learning vector calculus. He did partial derivatives. And then we had a whole afternoon together. This was him sitting, it was just us two and Lawrence. And I did actually grill him. I did actually make sure that he did not know. But actually to make sure that he is ignorant, just to make him clear that you don't know vector calculus. And this is what you don't know. And it was wonderful. He did take it on board. But he worked, he rose to it. I mean, he actually did try to, look at the maths and try to understand the maths. And in fact, this is us too. At the Cavendish laboratory. And in fact, these are the equations. And in the program, you will see he does try, and he does successfully describe these 4 equations. This is it. This is what life is all about, these 4 equations that you see in the background. And I think that was another wonderful journey that we went through. So I think to finish off, I just want to say that, questions key to curiosity. So this has been my journey to some extent, and I think it's all based on this jigsaw of asking various questions about the universe, some basic questions. But I think all of this has to fit in to a human understanding about what it means to be human. And I think it has to inform to a large extent of what that means. And these are all prismatic approaches that go into a higher dimension. So all this scientific or analytical world is a 2-dimensional, and I think somehow we've got to abstract it and put it into a 3-dimensional phenomena that seeps into that. And I think these 3 trips were based on that. So I think I'll stop there. Thank you very much.
I think you might know who I am by now, but I'm Will Self. I'm Professor of Contemporary Thought here at Brunel, and it's my job to thank Akram on behalf of the university, and I'm going to do that thanking, but first I think we've just got a couple of minutes. If there are any questions from the audience, I'll take those and relay them to Professor Khan quickly. There's a gentleman there in the kind of lower middle. Could you wait for the microphone, please? Because you can hear your voice inside your head, but we're further away.
I've got a personal question.
Yeah?
Do you think your proximity to proton accelerators has helped to turn your hair so distinctly?
Possibly.
Okay. But I also have a short sort of technical question. Can you help me try and understand the difference between X-ray tomography, positron emission tomography, and what you've just described as proton tomography?
Yeah, you could. I mean, what you could do also. I mean, there are certain forms of cancer which can't be you can't use protons or high energy particles like X-rays as well. And what you can do is you can put radioactive substances or tracers that can actually you can inject them into you, and then they will go towards where the cancer is to some extent, and then at some point they will decay into 2 particles, the positron and the electron, and then they will then try to kill off in specific, very difficult to reach regions within you to some extent. So that's slightly different, but the 2 are complementary. One, you could not use this technology for that type of cancer, but you could use the other type.
Yes, just in here. Could you wait for the mic? Could you wait for the mic?
Testing. Not too bad. When you talk about the Higgs explaining the property of mass, would it not be better to describe it as explaining the property of inertia, because it doesn't have anything to say about the equivalence of gravitational mass or energy, as far as an energy?
I mean, you could metaphorically say, well, it is inertia, you're absolutely right. I mean, it's the inertia to actually move forward. But a more interesting way of looking at it, which can be more fruitful, is to think of it in terms of an energy field to some extent. So both of them could be viewed. One is a much more technical and a much more useful definition. The other one could be more metaphorical definition to it. And which is good. I think metaphors are an interesting way in revealing different types of knowledge.
Anybody else?
Well, that's true.
The mic will be with you in 2 seconds.
You started by saying why.
Yes.
So I have a question to you. Why? As a layperson, why is it important for me to understand any of this?
Yeah. No. I mean, I think no, there is none. I mean, you should walk out and say, I don't need to know any of this rubbish. I mean, all of this is good for you, and you've had a nice time, and you've enjoyed that. But I think you've got to ask yourself one basic question, and that basic question is, what does it mean to be human? And if you can actually convince yourself that actually you don't need to ask the questions why, being a human, then you've got to ask yourself, well, what am I then? If I'm not actually driven in some way, it doesn't have to be technically, but in some way driven by this pathway, this sort of dense foliage or this forest, and discover new pathways as you're going through it. If that's not the general urge, then what are you?
This gentleman in the middle. Oh, no, we've got a gentleman here, and then we'll come to you. First.
Yes.
Do you remember 2 weeks ago, I was talking to you outside and trying to understand maths, and you were getting pretty exasperated.
Never.
Pulled the tablecloth off the table and prodded it and said,
Yeah.
the tablecloth is space-time, and I'm prodding it. What is the difference between space-time and the field you were describing? Is it the same?
I mean, I think it's...
You were talking about distortion.
That's right. That's right. I mean, I think a similar sort of analogy you can have, because you can also say that actually the Higgs field is like this. Yes, there's some sort of field out there. And all we are doing as physicists, we build these massive machines, and we're just getting these particles, these protons, at high enough energy. So they're very, very high energy particles, very point particles. And this is my wave. And all I'm doing is I'm hitting the wave or the field. I'm hitting the field. And this has to then rise. So there's some sort of perturbation, yeah? And if I can check that perturbation in my detector, then I've measured the actual field itself. That's what I'm doing. So high enough energy which hits the field creates the perturbation, and I can picture it. But the same thing in space-time. The space-time is exactly the same. So there's a space-time field that exists, and people try to hit that field as well and to perturb that field. And they call that the graviton. So we have the Higgs particle is the particle that corresponds to the Higgs field, and then there's the graviton that will be responsible for the space-time field itself. So there are these two different fields. And what you're doing is you're going from a continuous system to a more discrete system or description of the world out there. So you're absolutely right, yeah. Apologies if I was being...
Gentleman here in the middle.
That's that.
Akram, I started with possibly an answer to your question.
That's a good place to
Then
start.
I'll ask the question. You said, how do we get mass? And I thought that maybe nutritionists used to do with a lot of drinking and eating and all that. But more seriously, so I'm thinking of the diagram they put up with the electromagnetic wavelength, and you pointed out that the things that we see with our own eyes is a very small part of the spectrum. And we have all these things like microscope, accelerator, and whatever, many other things, radio telescopes, to look. But what I want to ask the question is that the knowledge that we create, and it is we create, is made up of then we expand the horizon through these instruments and other things. How do we know that? So we are making a mapping of what we know with what we don't know, and with these instruments. How do you know that when you're mapping those things, actually they represent the actual reality, rather than within our existing reality, we are just creating subclusters?
Yeah. No.
So i.e., how do we validate new, really new knowledge, which is not just, just epsilon different, but it's very vastly different?
No, that is a very, very good question. And then it goes back to this idea of what is our relationship with knowledge? I mean, what do you feel? What is the value that you attach to knowledge? And I think the scientific knowledge, as I try to highlight here, is one particular representation, is one particular schema. And schemas evolve. As you get new experiences, as you get older, you'll have a particular knowledge structure, but that's not important. I think it's the second order, the third order effects that actually shine different perspectives on the first order that you have. So there are many, many different representations of knowledge that one could have. And the question is, how do you bring it all together to create your own particular perspective of reality that's out there? And that's a lifelong endeavor. You can never say, well, I've got it, and that's it. And this is it. So I think, the whole journey that we're all on, to some extent, is a journey of discovery of ourselves. I mean, what is it that I do not know? I mean, to quantify your ignorance is a better way of saying it. Yeah, you want to work out how ignorant you really are. And these experiments actually are ways of jolting, are ways of awakening your own perceptions that, you have the truths or a truth.
The seed that gets going, the momentum gets going, everybody has a question.
When you are doing your research,
yes.
You see the order and the beauty.
Yes.
Do you ever get moments of humility and think, there is a God?
Yeah, no, that is, I mean, the word beauty, we've had many, many discussions, and especially in close confinements in a car, over 600 miles of discussion, gets even more complex, yeah? But, no, I think the most beautiful thing are the broken symmetries of nature. When symmetry is broken, you begin to see shards and windows into new ways of perceiving the world, and not in set patterns or set symmetrical principles. And the Higgs particle that we saw was a system that broke the symmetry of the standard model. And we saw this new reality to some extent. So I think, now whether, and what was the second part? Do I believe in?
I've lost my mind.
No, go ahead. It's God.
Do you have moments of humility and think,
humility, yes. Yeah. Well, I don't know about God, but certainly I have certainly humility. Yeah, you have it. You sit back and you think, I know nothing.
Yes, Newton said that.
And that's not. But then you don't fill it with something. You say you don't know anything, but then the next step isn't then to fill it with something. But then you say, well, actually, I don't know anything. Now I've got to go out there and try and understand. I've got to go and talk to people with different expertise or different forms of understanding, which is what we do at the university. And I think that's the richness. And then you get new forms of knowledge. But I think you have to be brave. You have to be confident to say, well, actually, to go to Peter, for example, and start talking to Peter about music, about Wagner, about, or to go to Will, in fact, and tell him what I think about Dante. It doesn't matter. You got to think, well, actually, I don't know, but I'm willing to learn. But the problem is having an open dialogue is very, very important. Not to have preconceived, well-defined dogmas which are sort of, put you into straitjackets. I think that's a beautiful place to be, and that really fills you up in many, many different ways.
Somebody over here? Yes, gentleman here.
Is energy associated with the fields that you've mentioned today? Yeah. And if so, where does the energy come from?
Yeah. Wonderful. That's an amazing question. Where does it all come from? No idea. going back there, I have no idea. I mean, there are ideas out there, conceptual ideas, theoretical ideas, but that's, yeah, you can become my PhD student anytime. And we'll work on it together, yeah. Wonderful.
Anybody else? Ah, yes, lady here. Run, fleet-footed microphone, Norman.
Thank you. Actually, mine's a question for Will. I was remembering, when you were talking about lines from a poem, I remembered some lines from a poem, which I think is Wordsworth. And the lines were, the world is too much with us, late and soon. Getting and spending, we lay waste our powers. Little we see in nature that is ours. What's the poem?
I'm not a great Wordsworthian, but I don't think that's Wordsworth.
No.
The meter sounds wrong for me. Tom?
I don't think it's Wordsworth.
No, it's not Wordsworth, is it?
Who is it? Is it Keats?
It sounds more like Keats
It's
to me.
perhaps Keats.
Yeah.
Perhaps Keats. But it just reminds me of
That's
something that you said. Because actually that was written a long time ago. And it's so pertinent now.
That's right.
Well, I mean, if I could actually take this opportunity to finish. Once the question slid on to me, but actually, you know, it makes one think of the Age of Wonder and the early period of the Enlightenment, when, of course, the arts and the sciences were very, very close together, and these cutting-edge romantic poets were writing about new scientific discoveries. And I have to say, as part of my vote of thanks to Akram, I came to Brunel 5 years ago, and Akram, Peter, other people here came and joined in this project, and Akram is as you see him. He is a marvellous, you know, the C.P. Snow said back in the 1930s that there were two nations in the country, and art and science didn't meet. Utter tosh. They meet in this man, as you've heard in the last hour. And when I feel humility, I think of Akram, actually, because his enthusiasm, you know, we make a lot here at Brunel about being collegiate, but this is Mr. Collegiate. He has no boundaries. He's interested in everything. He'll talk to anybody about anything, and he'll bring his knowledge. And working with him over the last few years, being engaged in these projects, for me, has been one of the most marvellous experiences of my professional life. So I'd like to thank Akram personally. I'd like to thank him this evening for a magnificent inaugural lecture. We're very, very lucky to have him. This is, as Jeff was saying, is the second of the inaugural lectures this year. They'll restart again in the autumn term. Details will be available on the website shortly beforehand, or if you're on our mailing list, you'll get details. Light refreshments, one of the most sinister combinations of two words in the English language, apart from bus replacement service, will be available shortly. But for now, could you put your hands together and thank the secretary?